So let's start. So essentially, in the last day, what we did was we were looking at complementation of NBW, right? So this was a main lemma which we looked at. So an NBWA rejects a word W if and only if there is an odd ranking for the run DAG. So we define the run DAG and we say that it rejects a word W if the run DAG corresponding to that word W, this has an odd ranking, and we defined the notion of a ranking function and so on. And then we also define the complement, the NBW which accepts the complement language. How? By, I mean, if we had an NBW with n states, then we are trying to guess a ranking function, an odd ranking function for the complement automaton, right? And what was the acceptance condition for that complement automaton? How did we define that? So the acceptance condition for the complement automaton. So we had the odd ranking function, and we also had something more. There was one more component, right? If you see here, it was like this.
It was something that every event state should be visible.
No,
I don't know.
it's the other way around, right? Because the event states should disappear because we are talking about an odd ranking function, right? So if the odd ranking function kind of like, so what happens in the odd ranking function? Like eventually it gets trapped in an odd rank, right? So you'll get to visit that odd rank infinity of. And here in this component, we were keeping the states which would have an even rank. And then this component you would like to disappear. You would like in the complement automaton, this should disappear. Like, so this should become empty, right? So, so this part should become then empty. This is the empty set. So that was the acceptance condition alpha prime for the NBW, which complements your input automaton, right? So this was the idea. And then we also talked about the size of this complement automaton. Like, what was the size of the complement automaton? Sorry?
2 power order n.
2 power order n log n, right? So because this is like, if you recall that this automaton was trying to guess such an odd ranking function, and the number of odd ranking function, it's like n raised to 2n plus 1, right? So because the odd ranks were from 0 to 2n, and also there was, yeah, I mean, there was also a bottom symbol, but roughly it was like, yeah, as you say, 2 raised to order n bottom, right? And so today we will start with, I will try to show that this upper bound that we have, this is kind of tight. I mean, in the sense that you cannot have a much better algorithm. We'll try to show a lower bound, which means that we'll try to construct a family of examples for which, when we are converting it, I mean, trying to get the complement automaton, right? Given this family of automata, when we are trying to get the complement automata, we are going to get almost some kind of a similar blow up in the state space. Is it okay? But if you recall that in the case of automata over finite words, you have a blow up of 2 raised to n instead of 2 raised to n log n, right? Here we are going to say that you are going to get something which is more than 2 raised to n. So that 2 raised to n log n is something we cannot really avoid. And as I think I mentioned in the last lecture, that that this lower bound that we are going to show, this is also not super tight, but if you again go back to that, like those lecture notes, which I would expect you to look at once in a while, you will find some references, and at least look at the introduction of these references, right? Like what those results are, even if you are not getting into the details of all the results and all, like at least it's good to know what those results are. Right. Uh, so we will start with this lower bound of NBW complementation. So I write down again some of the definitions here. So uh, we are going to talk about this, that there is a family of languages L1, L2, etc., such that LN is a subset of sigma and omega. So our alphabet is sigma n, right? If I'm talking about, so it's a family of languages, L1, L2, L3, like that. So why do I need to construct a family of languages instead of a single language? Why is it necessary that I need a family of languages?
So that we get a bounded in terms of n. Like, it's
Right?
separate.
So for example, like suppose if I give you a particular language and if I say that, let's say it has four states, right? And you can say, oh, 2 raised to n log n is like 2 raised to, let's say, 4, and log of 4 is like 2. So 2 raised to 8 is like 256, let's say, right? But 256, I could have also said like it's like 64 times 4, right? And which is like a constant c times n, 64 times n, right? But if we have a family of such languages, then it will show that, like this asymptotic upper bounds will, or yeah, asymptotic bounds will have. Clear? So that's why we need a family of languages, right? A single language does not suffice. Right. So here now we are saying that if you if we have such a family of languages such that like ln is a subset of sigma and omega, so the alphabet here is the size of the alphabet is also a function of n, right? If this can be recognized by an NBW with n plus 1 states, then every NBW which accepts the complement language will have at least n factorial states, right? I'm not just talking about 2 raised to n, but I'm talking about n factorial states, right? Which is again on in ego to n log, right? So this is what. So let's see how this family of languages will look like. So this is my sigma n, 1 to n, and then you have a shout symbol. And now I'm considering such an infinite word. I'm considering an infinite word W, and we associate a graph GW with this word. With this infinite word W, we are associating a graph GW. How? No, and so the set of vertices of this graph is from 1 to n. Okay, so we don't have the shard symbol in the set of vertices. So I have a word W, I have an infinite word W, and my sigma is n is 1 to n at the shard symbol, and corresponding to this infinite word, I have a graph where the set of vertices are from 1 to n. I don't have the shard symbol, right? And now I'm saying that the edge I comma j, it belongs to that graph. So there is a word, I'm having a graph G corresponding to that, or GW corresponding to that word W. And I'm saying that in that, so I have also defined the vertices, which are the vertices 1 to n. And I'm saying that an edge ij appears in the set of edges, ij appears in that graph if the subword ij, if the subword ij appears in W infinitely many times. Is it clear? If the subword ij appears infinitely many times in the word W, then I will have an edge ij in the graph, GW. Clear?
Is it like I and j consecutive or like
Yeah,
some?
it's consecutive. Yeah. So
Is it directed?
is it directed? Yes. Yeah. Okay. So I'll have that edge I to j if I and j are I mean j follows I. Okay. So yeah. Right. I mean, I think when you talk about, I mean, in the automata community, people don't always use the word subword. I mean, by subword, they also mean sometimes that it's not contiguous. I mean, it's not one after another. But people also use the word factor to define that, that these words are, I mean, they are contiguous to each other. Yeah, right. So, let's, for example, now I define the language LN. It's a set of such words in sigma n omega. So you recall that sigma n also had the short symbol, such that GW contains a cycle. Is it clear? So I'm defining ln as the set of words. It's the language of the set of words, such that if you consider the graph GW, it's a set of words W, such that if you consider the word GW, then GW will have a cycle, right? So you define your ln as this set. Okay. So for example, like if you consider sharp 1 omega, right? So here again, like you have some cycle. So let's say my n is 3, right? So I have 3 vertices, 1, 2, 3, and I have a cycle here because 1 appears infinitely many times. Clear? Now, if I consider instead of sharp 1 omega, let's look at the other example, which is, let's say, 2 1 followed by 1 2 3 omega. Correct? So what are the edges that I will have here in the graph?
2, 2, 3, and 3.
So I will have 1 2 2 3 and 3 1, right? So like this, 1 2 2 3 3 1. I also have a cycle here. Now if you consider 1 2 3 sharp omega, 1 2 3 sharp omega, right? Does it have a cycle? You have from 1 to 2, you have 2 to 3, you have, but then 3 to 1, you cannot go back, right? So I don't have a cycle. So this word should not belong to the language. Okay. Now, if you think a bit, you will be able to figure out that corresponding to that language LN, the automaton will look like this. It's not very difficult to figure out. So I'm not going to formally define the automaton. You can find it in the, like when I say I'm not going to define formally, I mean like defining all the edges, all the transitions and all those, but you can see how it looks like. Essentially, like you have for all the letters in sigma n, so you have a state Q0, which is the good state of the NBW or an accepting state. So what are we going to do? We are going to show that, so this particular automaton has n plus 1 states from Q0 to Qn, n plus 1 states. And we are going to show that any NBW which accepts the complement language will have at least n factorial states, right? So this is what we are going to prove. So this is the family of languages we are going to show the result with, right? So now how does it look like? So from Q0 to Q1, these are the states. And on Q1, you have a self loop on sigma 1. On Q2, you have a self loop on sigma n, and so on. From Q1 to Qn, you have self loops on sigma n. And again, sigma n has 1 to n as well as the sharp symbol. So this is my alphabet. And I also have a non-determinism from every Qi. In what way? Like from Qi, if I read the letter I, I'm here, as well as I can go to the state Qc. Okay, so there is a non-determinism. From Qi, if I read the letter I have a self loop as well as I can go to Q0. So now, suppose if let's try to get the intuition, okay, why this automaton accepts the language we are talking about, right? That you have in the W, if there is the cycle in the corresponding to the word W, if in GW you have a cycle, then this automaton should accept that word W. Why is it so? Can you look at this and tell me why do you think that? And if there is no cycle, it should not be able to accept. So you can think of maybe just any particular word maybe you can think of. Let's say that you start thinking about this particular word, sharp one omega, right? How will this word be accepted in this automaton? So each of them from Q1 to Q1, they are initial states, right? So when I put this arrow, this denotes that these are initial steps. So what is an accepting rank here for sharp one omega?
Q1 the sharp symbol, then 1 to Q1, then 1.
Yeah.
And then again same.
Right? So
Uh, hello, can you hear me?
yeah, I can hear it. Yes.
Yeah, so I can't see any sharp in this automata.
You cannot see any sharp in. Sorry. Yeah. Shanthan, go ahead.
Edges of this automata, like better in this in a word, right? So with sharp, I cannot see any edge in this automata, any transition with sharp in this automata.
No. So here, the set of letters on which you are making the
Oh, acha, okay,
sigma
yeah,
n,
okay.
and sigma n is the sharp symbol.
Yes.
Okay.
Sorry, yeah.
Okay. Good. So what I think, well, I mean, so one thing is like, okay, you can take to start with the sharp, and then you read a one, you go here, and then again you read a one, you come here, and again you read the sharp one like this, correct? So you are visiting this state Q0 infinitely often, right? Let's look at something more, maybe the second example. What about 2, 1, 1, 2, 3 omega? How can this be accepted? How can
So
this
after 2, 1, let's say we are at
be
2, 1.
in 1? So yeah, that's fine. So what you are suggesting is that after reading 2, you are in
Okay, so
this state.
yeah, after reading 2, 1, we are in this state.
Okay,
Yeah.
after reading 2, 1, you are in this state,
So
sure.
after 1, we will go to Q0.
So okay, you come after this one, you are coming to
Yeah.
Q0. Okay.
Then we will go to Q2.
Yes.
Then stay there. So
Stay
then
there.
we add the next one.
Yeah.
Then on the 2 we come back.
Come
and
back.
Then go to Q3.
Q3, right?
And then same way.
Yeah. So you wait for the next 3, you go
Yeah.
back, and then right. So there is a 3 on which you are coming, and then you wait for the next. So if you are coming to Qi, you wait for the next I when you go out, and then again you do it like that. Now, why will it fail here? Why will it fail here? So this should not be accepted by this automaton, right? As far as the way I'm claiming. Why will it not get accepted? So again, you can try to have a run for this word on this automaton, and why where we are going.
Same plan. When we are at Q3, we can't escape Q3 because of the sharp symbol.
You cannot, but you can stay here. Let's say, I mean, you are not able to escape, but you can stay here.
Okay. And then we will again have 1, 2, and
then you go back to here, like the 3. Maybe you might want to visit. You don't want to stay here forever, right? Because you have to visit.
If we go back after that, we can't
Read the sharp symbol.
Yeah.
Right? So you get stuck. So once you come here, then you cannot read the sharp symbol, because from Q0 there is no transition on the sharp symbol, right? You get stuck. So we are more or less convinced that this automaton accepts this language, at least this set of words we are talking about. Okay. So let's talk about a slightly more complex example. Let's say my aim is now 5. Okay. And this example will be useful when we are going to do the proof, right? Suppose my aim is 5, and I have a partition from 1 to 5. Sorry, I have a permutation of 1 to 5. which is like this one. This is pi 1. And I have another permutation of 1 to 5, which is 1, 2, 4, 3, 5. Right? And I'm saying that suppose, so okay, so here I'm saying that for any permutation pi, if I have pi hash, pi sharp omega, this is not going to be accepted by the automaton, correct? So this is not going to be accepted. Like just we saw 1, 2, 3 sharp omega is not going to be accepted because you come to Q0, you do not get a sharp symbol. If I have a permutation pi, any kind of permutation pi, pi sharp omega will not be accepted by this automaton, correct? So now instead of that, if I consider something like this, pi 1 sharp, pi 2 sharp omega. So where let's say my n is 5, my pi 1 looks like this, my pi 2 looks like this. And so I'm just talking about a specific case where n is 5, but this n can be anything. And I'm talking about these two permutations, but again, this can be any two permutations, right? So pi 1 sharp, pi 2 sharp. Will this word be accepted? It will be accepted. Why?
Because at the end of pi 1, we will be at Q2. And then we wait for the next two, which is in pi 2. And then we go back to Q0. And then say we come to Q4. Then
So, okay. So, yeah, could you, maybe I lost you somewhere in the middle, but could you start again? Like, what is the run you are talking about?
so like we did like just like we did earlier,
Mhm.
we traversed to pi 1, and then let's say we are at Q2.
Okay, so you are at Q2, and what are you reading now at Q2?
At Q2, I'm reading sharp, which is like pi 1 sharp.
So you have, so you are saying that suppose you have finished reading pi 1 and you are reading,
Yes.
and when you have finished reading pi 1, you are saying that let's say I am at Q.
Q.
Okay, so you read sharp, you are here. Okay, then
And then there is 1, I stay at Q2.
yes,
And then there is 2, so
Yes.
I move back to Q0.
correct.
And then
So you move back to Q0. Okay, after
and then I
reading
read 4, so I come to Q4.
Okay, after you read the 4, you come to Q4 somewhere here. Yes,
Yes. And then for 3, 5, and sharp, I stay in Q4.
3, 5, and sharp will stay in Q4. Correct.
And then after that, I read 1, 3, 5, 4.
Yeah, and then that 4 you will
At that 4, I go back.
go back to like this, right? So essentially here you can still find a cycle. There is a cycle in the underlying graph for this word. And can we argue why such a cycle should exist for a word of this form? Why such a cycle should exist? So let's see. I mean, this argument is not too difficult. So suppose, so what cycle we are talking about? It's a cycle. So there is an edge which appears in the graph. If the edge ij appears in the graph, if the factor ij appears infinitely often in the word, in the omega word, right? Here our omega word is this whole thing is the omega word, right? So now to show that indeed this word would contain a cycle. So let's say you have this pi 1, you have this pi 2. So there will be some, if this is a permutation, right? This is a permutation and this is a different permutation. There will be some index, let's say j, some minimal index j, where the letters would differ. The minimal index where the letters would differ. Here it is this position, correct? So here they are same, here they are different. So this is the minimum such position. I call it j, where the letters differ, right? Now, if it happens that the letters differ here, then the letter here, this letter that you see here, the 3, should appear at some position which is at some position k which is greater than j, right? In the second permutation. And similarly, this letter here in the second permutation should appear at some position L, right? Such that in the first permutation, such that these two letters are the same. Clear? Right? Now, if we have this, now we can try to see that there would indeed be a cycle with this thing, like, so suppose you start from, let's say, you start from here, like you see, you go from 1 to 3, like 3 to 5, 5 to 4. I'm putting all these edges, right? These edges I will put because they appear anyway infinitely often. I'm just trying to see if a cycle exists. Now 3 to 5, 5 to 4, and then 4 to 2 here. And then I can put this 2 to 4 because this 2 and 4 appear infinitely often. So I can have an edge from the vertex 2 to vertex 4. Clear? Because there is this 2 to 4, it appears here. And then again, like 4 to 3, 3 to 5, and this 5 here is the same as like the 5 here, right? So essentially what I'm saying, that because the 3 here is the same as this 3, and now I can directly go from here to this. I mean, this should have been even clearer. Rather than drawing this thing here, I should have actually drawn it like this. So I could have gone from here to here. Clear? Right? So you see that I'm getting a cycle. Right? So in fact, there can be more than one cycle. I mean, it's not necessary that I'll be having just a single cycle. As long as there exists a single cycle, this should be in the language. Right? So this word is accepted by this automata. Clear? Okay? Good. So now we will try to, any questions so far? Among the online participants, anybody? Any question? What we have looked. So now let's go to the proof. Okay, which will show that for every such ln, if you consider the complement language ln bar, any NBW which will accept that ln bar, the complement of ln, should have at least n factorial states. Right. So this is something we already saw, right? That pi sharp omega does not belong to. Like we saw this earlier. Here, right? Something like this. This does not belong. Okay. Now, this is just a definition. So we consider this NBW AN prime, okay, for recognizing the complement language, ln bar, okay. And so ln bar should accept this W pi. Clear? What is W pi? Again, pi sharp omega, where pi is a permutation of from 1 to n, right? So an prime should accept this because this does not belong to it. And let R pi be an accepting run of this complement automaton that we are trying to construct on W pi. And let the set of states which appear infinitely often in this accepting run be capital S pi. Clear? So again, what is S pi? So I'm saying that pi sharp omega, this is not in the original language again. So this should be in the complement language. And suppose I have an automaton accepting the complement language, I call it AN prime. Since it accepts this word, this omega word pi sharp omega, it should have an accepting run. And that accepting run should have should visit some set of states of AN prime infinitely often. I call that S of pi. I call that S of pi. Okay. Now, if I have two permutations like say pi 1 and pi 2 corresponding to these words like W pi 1 and W pi 2, I can consider S pi 1 and S pi 2. Okay. Now, my proposition is the following. This particular lemma says that for two different permutations, S pi 1 and S pi 2 should be disjoint. Okay. S pi 1 and S pi 2 should be disjoint. So I should be able to accept this complement automaton, should be able to accept all such permutations, and for every such permutation, the set of states which are visited infinitely often, they are all disjoint. So if we can prove this, this essentially gives us that the complement automaton should have at least n factorial states. Is it okay? Is it clear? It's a very simple pattern. Right. So we prove by contradiction, assume by way of contradiction that there is a state Q which belongs to both S pi 1 and S pi 2. Right? So if this is the case, we can define some finite words in the following way. We can define some words in the following way, that starting from an initial state, let's say you have some initial state, let's say Q0, okay, I have a run on a prefix like of the, okay, I can have a run on a word h, on a finite word h, which goes to Q. What is Q again? So Q be some state. By contradiction, I'm saying that there is a state Q such that Q belongs to the intersection of S pi 1 and S pi 2. It's a common state between S pi 1 and S pi 2. So I'm saying that suppose starting from Q0, I read something and I go to this state Q, right? So this should exist because it's a common state between S pi 1 and S pi 2. So I should be able to find such an image. Okay. And now I'm saying that I find another word, another finite word, U1, which will visit some alpha n prime. What is alpha n prime? So this is the set of good states for a n prime, right? It visits through some state in alpha n prime. So when I say alpha n prime, it visits, it means it goes through some state in alpha n prime. Is it okay? And U1 also has the whole permutation pi 1. Okay, clear? So I can also have such an U1. Why is it true? Why is it true? Why should I have such a U1? Why should such a U1 exist? So what is the definition of U1? Like you go to Q, and Q is a state which belongs to inf of that inf of run of pi 1, right? As well as inf of run of pi 2, right? Now I'm saying that I can have a finite word which starts from Q and comes back to Q by visiting one of the accepting states. And it also has the entire permutation pi 1. Why should such a U1 exist? Because Q1 is visited infinitely often, and since this pi 1 sharp omega is accepted by the complement automaton, it should visit one of the states in alpha and prime also infinitely often, right? So what I'm saying, like, so if I consider this W by 1, right, this word should visit some state in alpha and prime infinitely often, right? And it also visits Q infinitely often. So if I take a loop from Q to Q, if I take a large enough word from Q to Q, it should visit some state in alpha and prime, right? So I call such a word Q. Is it okay? So such a word U1 should exist. Okay? And now I say that I also consider another word U2 from another infix U2 of W by 2, another infix U2 of W by 2, such that reading U2 takes that run of the corresponding that pi to sharp omega, right? From Q to Q and includes pi 2. Okay? Is it okay? I mean, such an U2 should also exist. Clear? Any question? Any question by any of the online participants also? Right? So I should have such a U1, I should also have an U2. So note that in the U2 there's a small difference. I mean, I'm not claiming that the U2 has to visit the state from some state in alpha and prime. I'm not claiming that. I mean, in my when I'm defining U2, so there is a slight difference between the two. But you could also have this and have the same definition, symmetric. I mean, it wouldn't hurt the proof anyway. But I'm just saying that I would have had something like this, and this word should be large enough so that it contains pi2, and again u1 should be large enough so that it contains pi1. Okay, and such a u1 exists and such a u2 should also exist. Is it okay, or any doubt? Any doubt? No doubt? Okay, good. So now if I consider this word h u1 u2 omega. So what was h u1 u2 omega? I start from q0, an initial state. I reach q on h. I have such an u1 which visits a state from alpha and prime, and I have another finite word u2 which starts from q and comes back to q. Correct? Now if I consider h u1 u2 omega, is it easy to argue or is it easy to see that the word w, which is of this form, h u1 u2 omega, it belongs to L of an prime. Why? It visits alpha and prime infinitely often, right? And now I also claim that this word w belongs to L. Why? Similar argument to what we saw here, right? What we saw here, because u1 has this part, this pi1 here, and u2 also has the pi2 here. And exactly by this argument, we can find a cycle, right? So let's see this, right? Correct? So okay, so suppose my pi1 is of this form and pi2 is of this form, right? So can you try to find me the cycle? Now I'm saying that let j be the minimal index such that aj1 is not equal to aj2. So there must exist some k and l. There must exist some k and l such that j is less than k l and they are less than equal to n, such that aj1, right, is equal to ak2 and aj2 equal to al1. So this is what we saw. Now how will a cycle look like? Can you just, so from this, we just saw this, right? So just I want you to kind of formulate, write it a bit for me. How will the cycle look like?
So it will start from, say, AJ1.
Okay, so good. So let's start with AJ1.
Then it will go till A1L.
Very good. AL minus 1.
Which is also equal to AJ2.
So it is A1L, which is also equal to AJ2. Very good.
And then from AJ2, it will go to AK2, which is also equal to A1G.
Yeah. Right? So you see that we have got this cycle. Very good. So here and we have reached here. Right? So you can go like this and then again come out like this. Clear? So you have a cycle. So this word belongs to ln. The word w belongs to ln, as well as the word w is accepted by the complement automaton we were considering, right? So which gives a contradiction, right? So why do we have the contradiction? Because we assume by way of contradiction that there is a state q which belongs to both s pi 1 and s pi 2. So for every permutation, the set of states which are visited infinitely often should be disjoint, right? For a pair of permutations, the set of states which are visited by these different permutations, they should be disjoint, and hence any such automaton which accepts the complement language, right, complement of the language ln should have at least n factorial states, right? So we still have a gap, right, in the upper bound and the lower bound. In the upper bound, we showed something like how many states? Like it was 2n plus 1 raised to n, I think, right? 2n plus 1 raised to n. Here we are showing n factorial, right? So now you should go back to the notes, like I mean to the chapter, and tell me like what are the good results you found, right? Like so, it will have quite a few references to some papers, and given that it's a 300 level course, that's the expectation. I mean, at some point of time, I might decide that I may have some 10% weightage on this kind of class participation. I mean, when I say class participation, it means that you go back and like look at these things. And, okay, so this is important. Right. So any questions? So we kind of completed the NBW complementation, so which is a lot more complex compared to union and intersection, right? So we were looking at closure properties on NBW. So it was much easier to look at the closure properties with respect to union and intersection, whereas the complementation is much more complex, right? There's a blowout, which is right. If you have n steps, then you have 2 days to order n log n, and which we sort of see that it's kind of inevitable. Right? You cannot escape that. Okay. Any questions? So before I move on to the next thing. Right. Any questions from the online participants? No? Okay. So now we'll talk about determinization. Okay. So I think we mentioned on the passing, like we did not prove it formally, that like NBW cannot be determinist. So what was the language which we showed that to sort of argue that, I mean, that's what we are going to do it today formally, that there exists a language for which a DBW does not exist. So it's written here, finitely many ways, right? So if you consider infinitely many ways, so we saw that you can have a DBW, right? Whereas if you consider finitely many A's, we don't have a DBW is what we say, but today that's what we are going to prove formally. Okay. So here is the NBW for this language, that W has finitely many A's. So what would you like to do? Like if you have studied, you all have studied subset construction, right? Over finite words, for automata over finite words. Now, if you do the subset construction for exactly this automaton, you do the subset construction for this automaton, you get something like this. You get this automaton, right? You do the subset construction. So you take A, you stay here. You take B, you go to this set, right? Like because on B you can be in both Q0 and Q1, and then on A, since Q0 from Q1 there is no transition on A. From this, if you take an A, you come back to Q0, right? So this is the first thing you would try. If I ask you like, okay, are NBW closed under determinization, you will try to do a subset construction and see like, okay, what you get, and if you do this, then you get this. But now, what is the language that this is this DBW accepting? What language is this accepting? Infinitely many B's, right? Which is not the same as the one that we are looking for, finitely many A's. Why? Because if you consider AB omega, AB whole omega, it belongs to this automaton, right? Whereas it should not be there in the language that we are looking for. Now, just some observation, a key observation which will be useful later. So suppose there is a word W which belongs to the language A prime, right? So it implies something like, when does a word that is being accepted by this automaton, which we were not looking for this automaton. The subset construction gives us this automaton. When will this automaton that accept the subset that I mean when a word which is in the language of this automaton yeah, I mean, what can you sort of think of such a word, such an infinite word, in terms of, say, its finite prefixes? Is it clear, the question? I mean, so I'm saying that if a word which is accepted by this automaton, which we obtain by the subset construction, if a word is accepted by this, then can you say something about the set of finite prefixes for this word W?
Like you can get a prefix to as many B's as you want.
Yes. Yes. Yes, you are right. So one of the things, I mean, okay, I'll try to say is that, so if you see that there is a word W which is being accepted by this automaton, right? If a word is accepted by this automaton, then there are infinitely many prefixes. There are infinitely many prefixes, okay, for which you can find a run. There are infinitely many prefixes for which you can find a run in this automaton such that it will reach an accepting state of this automaton. Is it okay? Yeah. So what I'm saying is that, like, if you find that there's a word, there's an infinite word which is being accepted by this automaton,
Okay, we can get the prefix.
right? Then it will have this infinite word will have infinitely many prefixes. It will have infinitely many prefixes such that if you consider the run of those prefixes on this automaton, then they will I mean, yeah, if you consider a run, there will be an accepting run on this automaton, so which means that it will reach a final state here. So I'm talking about finite prefixes. So they will end in some final state in this original automaton. Okay. So for example, let's say I talk about AB omega. Okay. So I talk about AB, AB, like this. So there are infinitely many prefixes, AB, right? So if I consider the run, consider a run for this, a run for this, a run for this. So you can see that I can have a run like this, AB. I reach here in the final state here. If I consider AB, A, B, A, B, A, B, right? There are infinitely many prefixes for which there will be a run which will reach a final state here. Okay, but there's a catch. What is the catch? The catch is that these runs do not necessarily extend each other, right? Because this is a non-deterministic automaton, right? Though it is reaching of, suppose AB, I mean AB is a prefix of AB. But if you look at the run, which takes this to the accepting state, and if you look at the run which takes this to the accepting state, right? The run here does not extend the run here. Correct? Because it's here in the B, you see, you take this transition. Here, this B, you will still take this transition, right? So it's not so. So that's why I mean, even if it's the case that this word has infinitely many prefixes, and each of the prefix is ending in an accepting state, this word AB omega, right, is not accepted by this automata because you don't have a single run for which all the prefixes will follow that single run, right? Single run over this AB omega for which all the prefixes will follow that single run. Clear? So the runs don't extend each other. So you have infinitely many prefixes such that if you read those prefixes for this on this automata, there should be a run corresponding to that prefix, which will end up here, but those runs may not extend each other, right? So I just write that here. Okay. So yeah, this is what I was saying. Okay. Now I define. So I formally prove this. Okay. So there is a language L that is NBW recognizable, but not DBW recognizable. So what is that language? So it's like, so let's try to prove this. Let's try to prove this. So suppose L is a set of W such that W has finitely many S, and my sigma is A common, right? Okay. So now suppose I consider a word W, which is like B omega. I consider the word B omega, sorry. So B omega should belong to A. Clear? So I'm trying to prove this thing that indeed this language, for this language, there doesn't exist any B. So B omega belongs to L. So if B omega belongs to L, so suppose I have a set of accepting set of good states corresponding to yeah. Okay. So suppose I will say, suppose by contradiction, there is a DBW A prime that accepts K. Okay, suppose I'm trying to prove by contradiction. And suppose this A prime has a set of good states, which I call alpha prime. Now, if W belongs to this B omega belongs to is accepted by A prime, if B omega is accepted by A prime, then what happens? Like, so it should visit alpha prime infinitely often, right? So which means that there exists an index I1 after which you read I1 many B's, and so I will say some delta star Q0, where Q0 is an initial state. It should, sorry, it's a DBW, so it should be Q belonging to alpha prime. Is it clear? So if I'm accepting the word B omega, then of course it should visit the alpha prime, like the set of accepting states infinitely often. That means there should exist some I1, so that after reading those many B's, right, I1 many B's, I can go and reach a good state, which is a good state in alpha prime. Clear? So now you consider the word, sorry. Yeah, now you consider the word which is of the form BI1 A B omega. Right? You consider the word BI1 A B omega. This also belongs to L. So there are finitely many A's. This should belong to it. So then you should have another I2, BI1A, BI2, right? Such that why I'm writing delta star, because in general delta was defined on a letter. Like you start from a state on a letter, I'm calling delta star. It's just a standard extension. I mean, you have seen this in Automata over finite words, right? So like yeah, if I start from Q0, then this should also go to some maybe some Q prime like this, which should also belong to alpha. Correct? There should exist such an I, right? There I'm not writing all this such that here there exists I2 such that this should work. So now can you complete the argument? Can you finish the argument?
Suppose there are like K states in the DBW, then you keep repeating this process for like A plus 1 times. There should be some kind of repetition and you can loop it and say like A repeating infinitely many times also yes.
Well, you are almost right, but instead of saying that K states in DBW, you should say K states in alpha. K states in the alpha prime. Right? So what I think she was saying is the following, that if I do this, right, so I can get something like, I can read, suppose delta star, suppose, okay, so let's say my alpha prime, this is K. Okay. Now then what happens, like I can get some delta star Q0 B I1 A B I2 A B I J, okay, and then yeah, something I reach some state here, and if I okay, I mean if I read up to let's say K plus 1 such things, right? So I'm reading every time I read this BI1, BI2, I'm visiting some state belonging to alpha prime, right? And this I have done here K plus 1 many times, right? And there are at most K states in alpha prime, correct? So then by Pigeonhole principle, it means that there exists some J and let's say L less than equal to K plus 1, right? Such that some state in alpha prime is visited at least twice, right? So now you can consider, let's say, this part, which is this starting from, so you consider, let's say, B, I, J, and so after this you consider A, B, I, J plus 1, and something like B, I, L, right? So you just take the omega over this, and then okay, so the word that I'm saying is that the word BI1A, BI2, BIJ, A, BIJ plus 1, BIL, omega, right? So this should, like there are some A's also here. This should visit a particular state in alpha prime infinitely often. Okay, and see now this thing has infinitely many A's, right? So so this gives a contradiction. Okay, this gives a contradiction. Okay. Any question? Right. So I start with this word B omega, and then I can put some A's and I can see that there is this factor which can be repeated infinitely often, and that will have infinitely many A's. So if you have a DBW, which you say, you try to claim that DBW for this language finitely many A's, then we can indeed reach a contradiction. Okay, good. Now, we'll try to give some characterization. Any question? Is it okay? We'll try to give some characterization of when a language is DBW recognizable. When a language is DBW recognizable. We'll try to give some characterization, some understanding of that, right? So for that, we define something called the limit of a regular language. Limit of a regular language. So when I say regular language, I mean that it's over finite words. Okay. So consider a language R, and so we define the limit of R as a set of infinite words. Okay, such that a word W belongs to R if and only if there are infinitely many prefixes of W which belong to R. Clear? So the limit of a language. So what does the limit of a language, what does the limit operator do? It takes a language over finite words and it gives you a language over infinite words. Right? So R is a language over finite words. And you are getting a language over infinite words. Okay. So that's what. If W belongs to this limit of R, then W has infinitely many prefixes. So W here, it belongs to sigma omega, right? W belongs to sigma omega. It's an infinite word. Right. Right. So formally limit of word is a set of such infinite words, W1, W2, right? These are concatenation operators, like I'm concatenating them such that after reading each of these prefixes, you reach, or each of these prefixes, they are in the regular limit. Okay, so now this is exactly what I said, that limit is an operator that turns a language of finite words into a language of infinite words. Now, suppose R is a language of words that, so I just said something which is not quite correct. I mean, if you consider any R for over set of finite words, you can define the limit of R. I mean, it doesn't necessarily have to be a regular language, but we are going to use, when we are going to see the characterization, we use R as a regular language. So suppose R is a language of words ending with A. Okay. What is limit of R? Infinitely many, right? So that's the clear. So if R is a language of words ending with A, then the limit of R should be the set of words. This is a set of words such that W has infinitely many ways. Okay, good. Now we prove the following. Did you see what I wrote? You saw? Okay, so what did I write? Okay, but anyway, it's so what? So I'm saying that I'm going to give a characterization for the languages which are recognized by DBW, right? And we also saw something here, right? To give an intuition that this intuition, right? Like, let me try to increase the font a bit more. So W belongs to LA prime. It implies that it had infinitely many prefixes in that original automaton, such that the prefix says when you are reading, there is an accepting run ending in a final state of the original automaton. So now I'm saying that I want to give so keeping this in mind and having the definition of that limit of a regular language, right? But I also say that these prefixes don't necessarily, they extend, the runs on these prefixes don't necessarily extend each other, right? If they had extended, then what would you have, what would you think of, like if the prefixes, like the runs of these prefixes, they are extending each other, then if the runs on these prefixes, you have infinitely many such. So what I'm saying that in the subset construction, right, we have the subset construction, and what is there in this resultant automaton, right? If it has infinitely many prefixes for which you have runs here, and those runs here end in a final state here, but those runs may not extend each other for these different prefixes, right? But
If it extended, then we have it.
then you will have a dividend. Right. So good. So now I'm saying that given the limit of a language, right, you have understood the definition of a limit of a language. Now, can you think of a characterization in terms of the limit of a language and like languages which are accepted by a DBW?
I'm not sure if this is correct, but I feel like suppose the language has, okay, suppose R is regular, then we have an automatic DFA for R,
Right.
and then we could just, no, that's. I was thinking we could go from the final state to the initial state, so that would kind of make a.
Yeah, I mean, you are, well, thinking in the right direction, right? We are talking about, like we are saying that consider that the limit of a language, limit of a regular language. And you have a regular language, you can consider some kind of a DFA for that. You can consider the limit of that regular language, and you can also consider a DBW, right? A DBW also accepts infinite words. Now, can you have some kind of a connection between this limit of a regular language and a language which is accepted by a DBW?
That's a DBW, if it is the limit of something.
Exactly, right? So, so a language L is accepted by a DBW if and only if
It is the
limit of some regular language are, right? So that's what we are going to do. But before we do that, maybe can you tell me, like, when you see this automaton, the language accepted by this automaton and the language accepted by this automaton, right? Is it the case that one is a superset of the other, or they are not comparable or something? What do you think?
So L is contained in L of A prime.
L is contained in L of A prime, right? So if you have a word which is accepted by this, right? So which means that you will take the transition B at some point of time and like you will just keep on looping here. So this you can do here also, right? Like you just come here and then you just keep looping here. But in addition, what is happening is like here once you reach here, the A transitions are not defined, right? But here, for example, like you have the A transition, right? I mean, it's like the A transition will sort of take care of the fact that you actually did not even come here. You did not even come here. So the A transition will say that, okay, if I try to stay here itself, then where, I mean, I am taking the A transition from this state itself, right? And then, yeah, and then I just continue, right? So, yeah, I mean, one thing, maybe this can be a homework, which is like you should try to show that in general, not only for this particular language, but L is a subset of the language of A prime. Okay. Just in general, it's not very difficult to show. Like you are doing the subset construction and trying to prove that it's always the case that L is a L is a subset of that. LA, that A prime always accepts, accepts a set of words which are at least as big as a set of another set.
That will happen because
Yeah.
if we have an infinite accepting run for something in L,
Yeah.
the same run will work here because in the subset construction also we consider those accepted.
Exactly. Yeah. Right? Yeah. Okay. Good. Yeah, sure. Okay. So now, so this is what you said, right? A language L is DBW recognizable if and only if there is a regular language R such that L equal to limit of R. So let's consider this side first. So we have to prove both the directions, right? If and only. So if L is DBW recognizable, then we want to prove that there exists a regular language R such that to show that there exists an R such that what L equal to limit of R. Okay. How do I prove this?
Like, so L is DBW recognizable, so consider it's DBW.
Right.
Yeah, just that, like that will be the argument.
What? No, it is not complete. You were saying it correctly, but it's not complete yet.
It will be like a DFA. So all the prefixes will kind of be accepted by the.
Okay, so we have to prove two directions, right? One is that, so let's say you were right, like, so I can consider the DBW, consider a DBW A for L, right? And now I can think of, like, consider A as a DFA. Okay, let's say I call it AF, maybe, just to say finite words, right? AF. Now, so I want to say that, okay, and now suppose I say that L of AF, let's say, is R. Okay, and I want to prove that now my claim is that L is indeed limit of R. Okay. Now we have to prove two directions. A is a subset of this, and then we have to show this. Okay. To prove this, suppose W belongs to L. Right? So so suppose W belongs to L, so which means that W visits. So then W visits the good states. Suppose this is alpha, infinitely often. Right? Infinitely often. So now you look at all the finite prefixes which reaches that good state, and each of them will be in R. Hence, W belongs to limit of R. Okay. Consider all prefixes reaching alpha. Prefixes reaching alpha. Hence, and there are infinitely many such prefixes, which gives you that W belongs to limit of. Clear? What about the other direction?
Since if W belongs to limit of R, that means there are infinitely many prefixes of it,
Right.
which are accepted.
Right.
So that means it visits alpha infinitely many often. Because if a prefix is accepted, it ends at alpha. So now, since that word is visiting alpha infinitely many often, it belongs.
Well, so if it is in limit of R, that means there are infinitely many prefixes which are in R.
Yeah.
Right? But does it give you that the word will also see alpha infinitely many times. So you have infinitely many prefixes which are visiting alpha, the good states.
So, so there are at each extension it keeps visiting at each step. Keeps visiting.
So what property? I mean, could you say this for a non-deterministic automata?
Because of deterministic, the RAM can be extended.
Yeah, because it's deterministic, the RAM can be extended. So you see that it's important to consider that it's a deterministic automata, right? So you cannot have the same argument if you had a non-deterministic automata, right? Okay, yeah, good. So this I'm not writing then. I think it's clear enough, right? So any questions from the online participants for this direction? What about the other direction then? Okay, so the other direction. Okay. Yeah. Suppose that there exists a regular language R such that L equal to limit of R. Now we need to show that L is divisible. So how would you do this?
So again, consider the same DFA for it and think of it as a DBW now. And now whatever languages are accepted by that DBW are exactly equal to
Yeah,
limit
very
of
good. So let me try to just formalize this a bit. So suppose the language accepting R, suppose A accepts, or I mean, recognizes R, right? So there are again such things that often there are like you will find in the more formally in the textbook, you say that an automaton recognizes a language and it accepts a word, right? And you will find such things, I mean, rather than saying accepting a language and accepting a word. So it's sort of, I would say, it's more common to say like, the automaton recognizes a language and it accepts a word. And some people are very particular about it, not me though, but okay. So this automaton name, it recognizes. So it's over finite words, right? So now I consider, as you were saying, that let's say the word AB, just I'm looking at it as a DPW. And now I'm trying to say that, so my claim is, so AB is the DBW corresponding to A, right? So just I look at that automaton A and consider this as a DBW. And now my claim is that L of AB equal to L. Yeah, right, which is the limit of R. So this is my claim. Okay. So again, we have two directions. L of AB, your subset of limit of R, and the other direction. So how do I show this? So suppose it belongs to AB, so there is an infinite. So word which visits this infinitely many times, and hence like all these finite prefixes will visit the accepting states and right? And the other way around, again same. So there are infinitely many prefixes, and you can just consider their runs. The runs will extend each other, and then you have the word W, right?
Yeah.
If W belongs to, so essentially if W belongs to lim of R, this also implies W belongs to A of lim. Right? Okay, just by similar arguments. Any question? I went over this a bit fast, but I think it's not very difficult to kind of follow the very similar argument, both the directions. Okay, it's just, I mean, conceptualizing the lemma is the main thing, like to come up with the theorem that indeed the characterization is that a language L is DBW recognizable if and only if there exists a regular language such that the limit of that regular language is the same as ARM, right? In general, what we saw is that the L is a subset of that, right? This is what so yeah, I mean, when I'm talking about like yeah, so if I consider a word L, yeah, what I'm trying to say is that if instead of a DBW, if I consider an NBW, right, and consider that the underlying automaton, and you have a regular language considering that NBW, right? And if you consider the limit of that language, right? So the limit of the language, if it's an NBW, then it's a superset of that N, right? Where L is the language accepted by the NBW. So this is what we saw. But if it becomes DBW, then they are the same. Okay. Clear? Like I think. Is it okay? Yeah. Good. Okay. So right. So now we'll talk a bit about minimality. Okay. So and maybe we'll stop here. So one thing we would just like to see is that so if we consider, let's say, automata over finite words, we know that there exists a unique minimal deterministic finite automata, right? There's a canonical DSA, we call it. How do you obtain this? Like, do you know?
Equivalence class.
Equivalence classes, right? And there is some kind of relation we talk about, which is called the Myhill-Nerode relation, right? So you look at the Myhill-Nerode classes, right? Okay. So such equivalence relation does not exist for Büchi automaton, which will give you sort of deterministic Büchi automaton. So essentially what I'm trying to say is that such a nice characterization like a Myhill-Nerode characterization doesn't exist for automata over finite words. So the minimal automaton that you have, the minimal automaton that you get, it may not be unique, right? So suppose I give you this language, consider this language of infinitely many A's and infinitely many B's. So can you come up with a DBW corresponding to that? Can you just think of for a couple of minutes, and if you want to write on paper, you can also do that. But just infinitely many A's and infinitely many B's. It's a set of words. Every word should have infinitely many A's as well as infinitely many B's. So I want you to give a DBW corresponding to that.
So you could have two states, both are accepting states, good states, and like one has a loop over A, and one has a loop. Oh, we wanted DBW.
Yeah.
No,
Okay. Even if you have this, right? You are saying, wait, I mean, even if you are saying this, and you were talking about like what do you have like here?
that transition will be B.
B, okay.
And this other transition will be A.
Yeah. But this accepts like what are your initial states? Any of them?
Both are initial.
Both are initial. But this is not accepting what I'm saying because
I mean
it's a DBW first of all, right? It's a DBW. But this is like I mean, this
Three
accepts
states.
pretty much anything. Like I think this accepts all of sigma omega.
Yeah.
We'll need three states in some sense. So that third state will be the accepting state. And then from if we are at A and if we see a B,
Okay, so you are saying that you would need three states. Good. So how is the transition like?
okay, but it has to be determined. Okay, so let's say there's a self loop of A and a transition of B which goes to that accepting state.
Transition on B, it goes to an accepting state.
Yeah.
Okay, then
Now from this accepting state, if we see a B or a A whatever, we'll go to the third state.
so this is A and this is B.
Yeah. Yeah. And now here if we see a B, we will stay here. Once we see a A, we will come back.
Okay.
And then same here that when I see A or B, we will go back to the first state.
Okay.
And I'm not sure if this is minimal.
Huh?
There might be a two-state D, I'm not sure.
Yeah, I mean, so this is also something you can think of, like just try to find like, I mean, the brute force way of trying to see like if there exists a two-state deterministic Büchi automata for this language is to try out all the two-state automata, right? And here, essentially, I think you were right. So like you have some, you can start with some A's and then you see some B and then, well, this is not quite correct.
This is
because
not a DBW, right?
you can have like a B omega. It is right, but
Okay, so if we see A, then we will go back, and if we see a B, we will go ahead, something like that. This is how to determine it.
so what are you saying again?
Okay, it doesn't matter. If we see a B, we will go ahead, and if we see a A, we will come back.
Because right.
So what change do I do here?
That second arrow which has a A and B both.
You mean this one or this one A and B both?
The arrows, like in
Okay.
one we will put a A, in another we will put a B.
So you are saying here I put a B.
Oh no, but
It will work, no?
yeah, it will work. Yeah.
So what change do you want me to do?
Okay, in the first one put a B, the second one put a A.
So when you say first one, you mean this one.
Yeah.
A and here B.
So there are A and B both.
A B here A B both.
So just put A or just B, whatever.
Okay.
Like delete one of the things.
Okay.
And in the below transition which is AB, okay, then in the below transition put a B.
Put a B.
Yeah.
This is also not working, right? Because you have a B omega which is just accepting. And here also you have an A omega which is just
If we
accepting.
swap the B in, then I think B omega won't.
Oh yeah. We have to swap the B and
Then B won't hit it.
yeah.
Good only, na? We want
B and
Yeah, we don't.
yeah. Okay. Okay. So here B A and okay, seems like A followed by
No, this will be a subset, I think. Because this will kind of expect two consecutive A's or two consecutive B's.
no, not really, because you can come here B A
There.
like this A B A like yeah. So it seems to be working. Okay, you can also have another. Yeah, I think this is what you said. So you essentially like what this site does is like So you, well, I mean, I can also, yeah, I mean, it doesn't really matter which is the initial state, but I can also think of another similar automaton where I will have this as the initial state. And I'll just say that, okay, I start with an A, get some A's and come back with a B. So it's like this starting with A and then I have A and B alternating. Or I can have like starting with a B and then B's and A's alternating. I mean, it's just another way of thinking, but it doesn't really matter because have any of the states as an initial state. Another like, okay, so and another possible thing with three states is something like this. So what you said is this one, okay? And this is another one which is possible. So what you are doing that you start from here and then I can start with, let's say, read an AB, A or B, okay? And then again, I can read some B's here, I can read an A here. So there's an A here, there's a B here, there are some A's here, there are some B's here. I mean, you can just look at this. This also has like infinitely many A's as well as infinitely many B's you would need. You need to see several A's and several B's, right?
Yeah.
Like you can see some A's, you can loop here to see more A's, but then you have to see a B in order to come back. And then again, if you whatever, if you see a B here, you can see more B's here. You again have to see some A's and right. So this is not really like what I'm saying is that both of them have three steps. And now, I mean, it's not a unique kind of DBW states. And you can actually try to think and try to look at different possibilities. This language cannot be accepted by a DBW with just three steps. Okay, good. So that's that. And yeah, you can also have like the initial state can also change. And so you get like many such DBWs, which are not like, and this doesn't give you a unique minimum DBW really. Right? So this is this thing. Now, one final just note. So we are going to look at, like, so we saw that NBWs cannot accept something like a finitely many A's. But now if I say that I have a different acceptance condition where, I mean, it's just like you have infinitely many A's. So this was the language corresponding, sorry, automaton corresponding to infinitely many A's. But now I change the acceptance condition and I say that this is the set of states which you should visit only finitely often. So visit only finitely many times. Visit only finitely many times, right? So this is a deterministic automaton, but now I'm saying that this state you should visit only finitely many times. Then what will this automaton accept?
The number of A's are finite.
Exactly. So then it accepts, even though it is a deterministic automaton, it accepts the language of finitely many A's. So which you say like it's a complement language, right? And this is what we will call it a Ko-Bushi automaton. Ko-Bushi automaton. Okay. So we'll stop here and we are going to look at these different acceptance conditions in the next class, which will be on Monday. Okay. So any question from the online participants? Okay. Yeah.
We could have just, I mean, in this automata with three states, like this one drawn in blue color, right? On the left side. Isn't it sufficient to just say that since the start states are different, they are in fact distinct, minimal?
So, yeah, you are right. Like, so I'm saying that even if this has this start state, you could also have another automaton when you change the start state and so on. So these are distinct automata. You are right.
Makes sense.
Right. And all I'm saying is that, yeah, I mean, there exist other automata which is like even if you change the starts, I mean, irrespective of modifying the start state, I mean, you can still get which automata which look different. So that's what I'm saying. Yeah, but you were right. Like if you change the start state, it's a different automata.
Got it. Yeah.
Okay, great. Okay, so if there are no more questions, then I will maybe finish, stop the recording.